Empty space glows with heat if you accelerate fast enough. This is not science fiction, but a real prediction from the edge of our understanding called the Unruh effect. It is a mind-bending piece of quantum physics stating that if you could constantly accelerate, the perfect vacuum around you would stop feeling empty. Instead, you would perceive it as a warm bath of radiation, as if the void itself had a temperature. This is more than abstract theory. It is a key that unlocks profound truths about the fabric of our reality. By the end of this exploration, you will understand how this bizarre effect connects black holes, challenges Einstein, and whispers possibilities for technologies we can barely dream of. How can nothing become something just by moving faster, and whose version of reality is the true one, the person standing still or the one racing ahead? What does it say about our universe that the act of acceleration can literally heat up the void? The key to this strange warmth lies in a fundamental shift of perspective. For someone standing still in empty space, the quantum vacuum is just that, a void, the lowest possible energy state. But for someone constantly accelerating, pushing the engines harder and harder, that same empty space undergoes a dramatic transformation. It no longer feels empty. Instead, it appears to be filled with a gentle, uniform glow of warmth, a thermal bath of particles, specifically photons, radiating from every direction. This is the Unruh effect in its simplest form. The reality you experience is not absolute. It depends entirely on your motion. Acceleration literally rewrites the rules of the quantum world around you, turning nothing into something. We can even put a number to this bizarre phenomenon. The temperature of this phantom radiation is given by a precise, if intimidating, formula. Temperature equals Planck's constant times the acceleration divided by 2 pi times the speed of light times Boltzmann's constant. Now let us unpack that. Planck's constant is the fundamental unit of the quantum realm. Boltzmann's constant connects temperature to energy. The speed of light is our cosmic speed limit. What this formula tells us is beautifully direct. The faster you accelerate, the hotter the empty space around you becomes. The warmth is not an illusion. It is a real, measurable prediction of how quantum fields behave for an accelerating observer. To make this concrete, picture our astronaut from earlier, not just floating, but now strapped into a ship with its engines locked on. As the ship accelerates at a constant rate, say 1 gravity to feel like home, the astronaut would theoretically perceive the infinite blackness outside the viewport as subtly warmer. It would be an impossibly faint glow, far too weak for any human to ever feel, because the accelerations required to produce a noticeable temperature are astronomically huge. But the principle remains. A universe of silent, invisible energy becomes perceptible as heat, simply because the observer is choosing to move in a very specific way, to push against the fabric of spacetime itself. This raises a profound question. If the vacuum can appear warm to one person and cold to another, whose reality is the true one, this apparent contradiction between two realities forces us to ask a deeper question. What exactly is this empty space that can appear so differently? To understand the warmth an accelerating astronaut feels, we must first peer into the true nature of a vacuum. In our everyday world, a vacuum means nothing is there. You pump the air out of a chamber and you are left with emptiness, but in the quantum realm, this idea of true emptiness completely shatters. According to quantum field theory, the foundation of modern physics, what we call a vacuum is anything but empty. It is a seething, bubbling, energetic foam, alive with possibility. This is the stage upon which the Unruh effect plays out. Think of the fabric of space not as a smooth, still pond, but as a turbulent ocean during a storm, with waves constantly rising and crashing. At the tiniest scales, pairs of particles and their antimatter counterparts, known as virtual particles, are constantly flickering into existence. They borrow a tiny amount of energy from the vacuum itself, exist for an almost impossibly brief moment and then annihilate each other, returning the energy. This endless dance of creation and destruction is called quantum fluctuations. They are not particles in the way we normally think of them. You cannot catch one in a box. They are more like ghosts or shadows of particles, transient disturbances in the quantum fields that fill all of space. For an observer at rest, these fluctuations are perfectly balanced and completely undetectable. They come and go so quickly that they leave no net trace, no energy you can measure. The vacuum appears quiet and cold, but introduce constant acceleration, and this balance is disrupted. From the perspective of someone accelerating, the very act of moving faster and faster through this quantum foam changes how they interact with these fleeting virtual particles. Some of these ghostly pairs, which would normally vanish before being noticed, get stretched out. The acceleration effectively gives them a little more time, a different viewpoint, and from that rushing frame of reference, they no longer perfectly cancel each other out. Instead, they manifest as real, detectable radiation, the gentle thermal glow of the Unruh effect. So the warmth is not created from nothing, it is always there, woven into the fabric of space itself as potential. Acceleration is simply the key that unlocks it, transforming the hidden, seething activity of the quantum vacuum into something an observer can literally feel as heat. The ghostly warmth of the Unruh effect emerges from a boundary in space itself, a line drawn not by matter but by motion. This is the Rindler horizon, and it is the true reason why acceleration rewrites reality. Picture our astronaut again, accelerating at a steady pace through the void. From their perspective, something strange happens behind their ship. A boundary forms, an invisible wall in space that forever recedes as they accelerate, but which they can never, ever reach. Nothing, not even light signals sent from beyond this point, can ever catch up to the accelerating ship. This is the Rindler horizon, and it acts just like a black hole's event horizon, but for acceleration instead of gravity. It is a point of no return for information. Now, remember the quantum foam, that seething sea of virtual particles popping in and out of existence all around us. For an observer at rest, these fluctuations happen everywhere in a perfectly smooth and symmetrical dance. But for our accelerating astronaut, the Rindler horizon brutally cuts that smooth quantum field in two. It creates an absolute division between the region of space the astronaut can still interact with and the region that is now forever hidden. This division is not passive. The constant acceleration, the relentless push against the fabric of space-time, violently scrambles the information contained in those quantum fluctuations near this new horizon. The delicate, balanced pairs of virtual particles get torn apart by the physics of this boundary. One member of the pair can fall behind the horizon, lost forever to the observer, while its partner is left stranded in the observable region. That stranded particle is no longer virtual. From the astronaut's point of view, it is now a real particle, a piece of real radiation. And because this process happens constantly and randomly across the entire horizon, what the astronaut perceives is not a few stray particles, but a uniform, gentle bath of warmth coming from all directions. The heat is not magic, it is the thermodynamic signature of lost information. The acceleration, by creating a horizon, permanently severs the astronaut's connection to part of the universe. That loss of connection, that scrambling of quantum information, manifests as energy, and that energy is what we feel as the Unruh warmth, so the void does not spontaneously heat up. Instead, the act of accelerating carves a hole in your observable universe, and the quantum cost of that cosmic amnesia is paid to you in thermal radiation. This staggering heat from the void comes with a price tag of unimaginable speed. To decode the Unruh effect's formula is to confront a universe that operates on scales far beyond our human experience. The temperature of the phantom radiation depends on one thing above all: how hard you are pushing. The relationship is beautifully simple. The faster you accelerate, the hotter the empty space around you becomes. But this simplicity hides a devastating reality. The numbers involved are not just large, they are cosmically, incomprehensibly vast. Let us put it in practical terms. Imagine you wanted the vacuum to feel just 1 degree Kelvin above absolute zero, a temperature so cold it is barely a whisper of warmth. To achieve that, you would need to accelerate at a rate of approximately 2.5 times 10 to the 20th meters per second squared. To grasp that number, compare it to the gentle pull you feel every day. Earth's gravity, the force that keeps you in your chair, is a modest 9.8 meters per second squared. The acceleration needed for a 1 degree Unruh glow is over 25 billion times stronger than that. It is an acceleration so violent that no material object, no structure made of atoms could possibly survive it. It would be instantly and utterly vaporized. This is why you do not feel a warm quantum glow when you slam the pedal in a sports car, or even during the intense launch of a rocket. The forces involved in all of human engineering are like a gentle breeze compared to the hurricane required to make the vacuum's hidden energy perceptible. The Unruh effect is not something you can experience directly. It is a prediction that lives in the extreme realm where quantum mechanics and the structure of spacetime itself begin to merge. It is a phenomenon of horizons and relativity, a signature written in the fabric of the cosmos that requires, for us to read it, energies and accelerations found only near the most violent objects in the universe or in the most delicate experiments ever conceived by physics. This immense gap between the formula's elegance and its practical requirement tells us something profound. The Unruh effect is not about our everyday reality. It is a lighthouse guiding us toward a deeper understanding of reality's absolute limits. This profound link between acceleration and heat reveals a secret twin in the cosmos. The Unruh effect is not an isolated curiosity. It is the conceptual mirror of one of the most famous predictions in modern physics, Hawking radiation. These two phenomena are born from the same quantum principle, just dressed in different cosmic attire. Stephen Hawking stunned the world when he calculated that black holes are not perfectly black. Due to quantum effects at their event horizons, they should glow with a faint thermal radiation, slowly evaporating over astronomical timescales. For decades, this seemed like a unique and bizarre property of gravity's ultimate victory. But the Unruh effect shows us it is not unique at all. It is part of a universal rule. Both effects stem from a horizon scrambling the quantum vacuum. In the Unruh case, the horizon is created by motion, the Rindler horizon of constant acceleration. In Hawking's case, the horizon is created by gravity, the event horizon of a black hole. In both scenarios, the existence of a boundary that hides information forever forces the quantum fields to reconfigure. Virtual particle pairs are torn apart by the physics of the horizon, with one member lost forever and the other escaping as real, detectable radiation. The result is the same, a bath of warmth where there should be only cold emptiness. This connection is not just a neat coincidence, it is a foundational insight. It tells us that temperature, information loss, and horizons are deeply intertwined concepts in the fabric of reality, whether you are accelerating in empty space or falling toward a singularity. For physicists, the Unruh effect is an invaluable gift because it provides a simpler, more manageable model. Hawking's calculation is fiendishly complex, dealing with the wildly curved spacetime around a collapsing star. The Unruh effect, however, plays out in the flat, predictable spacetime of special relativity. By studying the thermal glow of an accelerating observer, scientists can gain crucial intuition about the more intimidating physics of a black hole's glow. It is like learning the principles of aerodynamics in a wind tunnel before designing a supersonic jet. The Unruh framework allows researchers to ask, if this is what happens when acceleration creates a horizon, what changes when gravity does the same job? This twin relationship elevates the Unruh effect from a fascinating thought experiment to a vital theoretical tool, a guiding light in the quest to understand how quantum mechanics and gravity might finally be reconciled. Yet this elegant idea did not appear from the void itself. It emerged from the mind of a physicist, William Unruh, in 1976, during a period of extraordinary upheaval in our understanding of the cosmos. The intellectual atmosphere was electric. Just 2 years prior, Stephen Hawking had dropped a bombshell, proposing that black holes could radiate heat and eventually evaporate, a stunning marriage of quantum mechanics and gravity that left physicists scrambling to understand its deeper meaning. Bill Unruh, a Canadian theorist, was diving into these very questions, exploring the profound analogies between thermodynamics, acceleration, and gravity. He asked a deceptively simple question: if a black hole's gravity creates a horizon that radiates, what does constant acceleration, which also creates a horizon, do to the quantum vacuum? Working through the complex mathematics of quantum field theory from the perspective of an accelerating observer, Unruh performed a brilliant piece of theoretical deduction. He showed that the vacuum state, which looks empty to someone at rest, would not look empty at all to someone in constant motion. Instead, that observer would find themselves immersed in a thermal bath of particles. It was a startling prediction, one that extended Hawking's revolutionary insight into a new and unexpected domain. Unruh's calculation was not about massive stars collapsing, but about the very nature of empty space and motion itself. He demonstrated that this thermal glow was an inevitable consequence of quantum theory and Einstein's special relativity working in concert. His work expanded the paradigm, suggesting that temperature was not an intrinsic property of an object, but could be a property of an observer's journey through the quantum fields of the universe. It was a humble yet monumental addition to physics, a key that helped unlock the deeper unity between seemingly disconnected phenomena, forever linking the heat of acceleration to the heat of a black hole's demise. This beautiful symmetry between motion and heat forces us to confront a startling question about reality itself. If one person feels a warm glow from the void and another feels nothing, which experience is the true one? This is not a minor technicality. It is a deep and ongoing debate at the very heart of interpreting the Unruh effect, splitting physicists into two compelling camps. On one side, you have the realists. They argue that for the accelerating astronaut, the radiation is utterly real. It would interact with their instruments. It could theoretically be measured. It carries real energy. From that rushing frame of reference, the thermal bath is as physically real as the warmth from a cup of coffee. The vacuum has a different, warmer state for them, and that state is just as valid as the cold vacuum of the stationary observer. There is no single God's-eye view of the universe, only perspectives, and each perspective has its own equally valid physical reality. The warmth is not an illusion, it is the authentic consequence of their motion through the quantum fields. The other side offers a more cautious, instrumentalist view. They suggest the radiation is a perceptual artifact, a consequence of how the accelerating observer's measuring apparatus couples with the quantum field. It is real in the sense that it gives a real measurement, but it does not mean the vacuum itself has fundamentally changed for everyone. From this viewpoint, the real state of the field is the cold vacuum of the inertial or non-accelerating observer. The heat detected by the accelerating astronaut is like a mirage created by their own strenuous motion, a trick of perspective rather than a change in the fabric of space. So, who is right? The debate cuts to the core of what physics actually describes. Are we mapping an objective, external reality, or are we merely charting the consistent interactions between observers and the universe? The Unruh effect sits at this crossroads. It suggests that concepts we think are absolute, like empty space or even particles, might not be fundamental properties of the universe, but rather relationships between an observer and a quantum field. There is no single answer yet, and perhaps there never will be. But the very existence of the argument illuminates a profound truth. Our universe is not a static stage. It is a dynamic, participatory arena where the act of observation, and even the state of motion, is woven into the very definition of what is real. The warmth of the void might be the ultimate litmus test, asking us not just about physics, but about the nature of existence itself. The debate over reality may be philosophical, but the need for evidence is absolute. So how do you test a prediction that demands acceleration strong enough to shred planets? This is the monumental experimental challenge of the Unruh effect, a quest to measure the seemingly unmeasurable. Direct detection in any traditional lab is for now a fantasy. To produce a warmth even a sensitive thermometer could register would require forces billions of times beyond what any particle accelerator or material could withstand. The numbers are so astronomically out of reach that physicists had to get creative. They asked a brilliant sideways question: what if we could not go to the extreme physics, but could instead bring a version of that physics to us? This gave birth to the field of analog gravity. The core idea is to find another physical system, something we can control on a tabletop, whose underlying equations mirror the mathematics of an accelerating observer in a quantum field. If the math is the same, the phenomena should be too. It is like using ripples in water to understand the principles of sound waves, even though water and air are completely different substances. One of the most promising analogies involves something called a dumb hole or sonic black hole. Imagine a fluid flowing faster and faster until it surpasses the speed of sound in that fluid. Just as nothing can escape a black hole's event horizon once it passes the point where light cannot outrun gravity, in this supersonic flow, sound waves cannot travel back upstream. This creates an acoustic horizon. Researchers can then probe the quantum fluctuations in this fluid, and the prediction is that an analogue of Hawking radiation, and by extension Unruh radiation, should appear as faint ripples of sound or heat at that horizon. Other ingenious setups use superconducting circuits where microwave photons play the role of particles, and carefully engineered magnetic fields create effective horizons. Or they employ Bose-Einstein condensates, clouds of atoms cooled to near absolute zero, where the atoms move so slowly that scientists can manipulate them to simulate the stretching of spacetime itself. In these ultra-cold atomic lattices, researchers can essentially program an acceleration into the system and watch how the quantum fluctuations respond. While none of these experiments detect the original Unruh radiation from the vacuum of space, they are hunting for its unmistakable twin, the telltale signature of thermal radiation born from a horizon. A successful detection in any of these analog systems would be a monumental validation. It would prove that the underlying quantum mechanism is sound, that when you create this specific type of informational boundary, you pay a thermal price. It would move the Unruh effect from a beautiful theoretical prediction to an observed principle of nature, confirming that the strange link between acceleration, horizons, and heat is not just a mathematical quirk, but a fundamental feature of our reality. The most promising path to evidence does not lie in conquering impossible speeds, but in a clever act of cosmic mimicry. This is the realm of analog gravity, where scientists build miniature, metaphorical black holes right here on Earth. The goal is not to recreate the immense gravity of a collapsing star, but to replicate the essential mathematical conditions that give rise to an event horizon. One of the most elegant methods uses something surprisingly familiar: flowing water. Imagine a channel of water, smooth and fast. Now, imagine increasing the flow until the water rushes downstream faster than the speed of sound in that water. This creates a point of no return for sound waves. Any ripple, any sonic disturbance that forms downstream of this point cannot travel back upstream against the overwhelming current. It is trapped. This boundary is an acoustic horizon, a sonic black hole, often called a dumb hole. Just as light cannot escape a gravitational event horizon, sound cannot escape this acoustic one. Here, the gentle lapping of water waves stands in for the flickering quantum fields of empty space. The quantum fluctuations in our fluid are tiny, spontaneous ripples of sound. According to the analogue, the powerful flow at the acoustic horizon should tear these virtual sound ripples apart. One part of the ripple gets swept away downstream, past the horizon, lost forever. The other part is converted into a real, detectable sound wave that radiates outward. These are phonons, the particle-like packets of sound energy. From the perspective of the fluid itself, sitting still in the lab, nothing special happens. But from the theoretical perspective of something floating along with the flow, experiencing the accelerating current, the horizon should emit a faint thermal glow of sound, a sonic version of Hawking or Unruh radiation. By meticulously measuring the phonons that emerge from such a setup, physicists are not detecting the Unruh radiation of space itself, but they are testing the universal engine that produces it. They are asking, if we create a horizon in this controlled system, does it pay the predicted thermal price? A clear, measured signal of thermal phonons would be a resounding yes, proving that the fundamental marriage between horizons, quantum fluctuations, and heat is a robust feature of nature, not just a theoretical fantasy. It turns the abstract mathematics of accelerating frames and curved spacetime into something you could, in principle, hear with a sensitive enough microphone, a whisper of heat born from a river of sound. This connection between horizons and heat reveals a deeper quantum strangeness woven into the effect. The phantom radiation an accelerating observer feels is not just warm, it is deeply entangled. This means the particles of Unruh radiation are born in pairs, their quantum states linked across space in that spooky action at a distance that so troubled Einstein. If you measure one, you instantly know the state of its partner, no matter how far apart they have flown. But here is the twist: acceleration does not just create this entanglement, it can also brutally tear it apart. Imagine two particles, Alice and Bob, that start their journey perfectly entangled in the cold vacuum of empty space, as seen by a stationary observer. Now set Alice on a path of constant, blistering acceleration. From her rushing perspective, she is plowing through that thermal bath of Unruh radiation. Those new particles she perceives are constantly interacting with her and, crucially, with her original entangled partner, Bob. This interaction acts like a form of quantum noise. The relentless buzz of the thermal environment scrambles the delicate quantum link. From Alice's accelerating frame, her precious entanglement with Bob degrades or even completely disappears. It is as if the heat of her motion creates a static that drowns out their quantum connection. This has staggering implications for a future built on quantum technology. Quantum computers and ultra-secure quantum communication networks rely on maintaining pristine entanglement between particles. But what happens if one part of your quantum satellite network, or a component of a computer, is undergoing significant acceleration? The Unruh effect suggests that the very motion required to position that technology could introduce a fundamental source of error, a thermal noise from the vacuum itself that corrupts the quantum information. It forces engineers to ask new questions. Could the vibration of a spacecraft or its orbital acceleration be enough to measurably impact quantum bits? For missions that aim to create entangled networks across the solar system, this is not just theoretical, it is a practical design hurdle. The universe, it seems, has a built-in tax on quantum coherence for anything that chooses not to sit still. This transforms the Unruh effect from a cosmic curiosity into a potential engineering specification, a whisper from the vacuum that must be accounted for in the blueprints of tomorrow's most advanced machines. The static from the vacuum that threatens quantum entanglement points to an even more profound possibility. Perhaps this quantum noise is not just a side effect of acceleration, but its very source. This leads us to a radical question, one that challenges the bedrock of classical physics. What if inertia, that familiar feeling of resistance when you push on an object, is not an intrinsic property of matter at all? What if mass itself is an illusion, a collective effect born from an object's interaction with the seething quantum vacuum? This is not mainstream physics, but a fascinating and controversial frontier. The idea finds its roots in the philosophy of Ernst Mach, a physicist who argued that an object's inertia is not a property of the object alone, but arises from its relationship with all the other mass in the universe. In a Machian view, if you were alone in an otherwise empty cosmos, pushing on a rock would meet no resistance at all. Its mass, its inertia, is conferred by the distant stars. While Einstein was deeply inspired by Mach's principle, it was never fully realized in his theory of general relativity. But what if the distant stars providing this cosmic drag are not far off galaxies, but the infinite, energetic quantum fields right here in the vacuum? Enter a speculative but compelling framework known as stochastic electrodynamics, or SDE. Proponents of this model propose that what we perceive as empty space is actually filled with a real, classical background of random electromagnetic waves, a roiling sea of zero-point energy. In this picture, when an object tries to accelerate, it doesn't glide smoothly. It plows through this electromagnetic froth. The waves buffet the object from all sides when it is at rest, creating a balanced pressure. But when it accelerates, the Doppler effect changes that balance. Waves hitting the object from the front appear blue-shifted, carrying more momentum, while waves from behind are red-shifted. This creates a net pressure pushing against the direction of acceleration. That resistance to motion, according to SDE, is what we experience as inertia. And here is where the connection sparks. The Unruh radiation an accelerating observer sees is a thermal, quantum version of this same imbalance. The warmer glow from ahead represents those higher energy, blue-shifted vacuum fluctuations. So while the full SDE model is distinct, the conceptual link is powerful. Both suggest that inertia is not something you carry with you. It is something the universe imposes on you as you move through its hidden energetic substrate. An object's stubborn refusal to change its speed may not be a property of its elementary particles, but a collective drag force from the quantum sea itself. If true, this would be a monumental unification. The laws of motion described by Newton centuries ago would emerge directly from quantum field theory. Mass would cease to be a fundamental tag on a particle and become a dynamic relationship, a conversation between matter and the vibrant, energetic void it moves through. We are far from proving such a revolutionary idea, and it remains a minority view, yet it stands as a testament to the power of the Unruh effect to inspire. It pushes us to ask if the most familiar forces in our daily experience are, in their deepest essence, quantum thermodynamic phenomena, the gentle heat of the vacuum made manifest as the resistance of the world. The dream of a fuel-less engine has haunted science fiction for a century. What if the Unruh effect offered a path, not by defying physics, but by embracing its deepest quantum truths? The theoretical concept of an Unruh thruster is the ultimate expression of this dream. Imagine a spacecraft that doesn't carry its own fuel. Instead, it finds a way to interact with the very thermal bath it creates by accelerating, somehow converting that phantom radiation into a net push. The principle sounds almost circular. You accelerate to create the radiation, and then you use that radiation to sustain the acceleration. It is the idea of pulling yourself up by your own quantum bootstraps. In this speculative vision, the thruster wouldn't be pushing against anything external like a rocket plume. It would be engaging in a complex dance with the quantum vacuum itself, perhaps by asymmetrically emitting or absorbing the Unruh radiation in a way that creates a directional bias, a gentle but continuous pressure difference. The ship would essentially be surfing the thermal gradient of its own making, a gradient that exists only because it is moving. This isn't about creating energy from nothing. It would be a machine that cleverly transduces one form of energy, the work done to initiate acceleration, into a sustained interaction with the vacuum's latent potential. For a moment, set aside the monumental barriers and consider what this would mean. A true Unruh-driven vessel would have no need for propellant tanks. Its range wouldn't be limited by how much fuel it could carry, but by the endurance of its systems and the patience of its crew. It hints at a future where crossing interstellar space isn't about explosive chemical burns, but about a smooth, constant, whisper-quiet push against the fabric of reality itself. The ship's engine glow wouldn't be a fiery plume, but a subtle, ethereal warmth emanating from its hull, the visible signature of the quantum sea it is stirring. Yet this beautiful dream crashes against the brutal wall of physical reality. The accelerations required to produce a measurable Unruh effect are, as we have seen, astronomically huge. To generate even a minuscule amount of thrust from this mechanism, you would need to sustain accelerations on the scale of the Planck acceleration, a number so vast it is essentially the universe's ultimate speed limit for changing velocity. At those levels, the thermal bath would be unimaginably hot, far beyond any material's ability to contain or harness it. Any structure, any atom, would be instantly vaporized by the very energy it was trying to use. Furthermore, the efficiency of such a process is deeply questionable. The energy required to create the acceleration in the first place would almost certainly be far greater than any trickle of thrust you could recover from the Unruh radiation. From an engineering standpoint, with our current understanding, it is a closed loop with catastrophic losses. So why even entertain the thought? Because it pushes the boundaries of what propulsion means. It forces us to ask if a rocket is the only way to move through space, or if there might be more subtle, field-based methods waiting to be discovered. While a literal Unruh thruster may forever remain in the realm of thought experiments, its value is in the questions it raises. It connects the dream of starflight directly to the quantum nature of empty space, suggesting that if we ever learn to truly engineer the vacuum, the rules of the journey may change in ways we cannot yet fathom. The sheer impossibility of harnessing that phantom heat reveals a deeper truth about the quantum void. The Unruh effect is a precise, narrow window into a far grander and more chaotic phenomenon, the ocean of vacuum energy itself. This is the zero-point field, the foundational hum of the universe, the reason empty space is not empty. It is the source from which the Unruh warmth briefly condenses, but it is crucial to understand the distinction. The Unruh effect is not a general blueprint for free energy. It is a specific, observer-dependent consequence of moving through this field in a very particular way. To mistake one for the other is to confuse a single ripple for the entire sea. The zero-point field is the lowest possible energy state of a quantum field, but lowest does not mean zero. Due to the Heisenberg uncertainty principle, which forbids perfect stillness, every point in space buzzes with a finite, irreducible energy. Think of it as the universe's background static, a ceaseless, invisible vibration that permeates every cubic centimeter of existence. This isn't speculative. Its effects are indirectly confirmed through phenomena like the Casimir effect. Here, two uncharged metal plates placed incredibly close together in a vacuum will be gently pushed together. Why? Because the plates restrict the kinds of quantum fluctuations that can exist in the narrow gap between them. Outside the plates, all wavelengths of the zero-point field can flicker freely. Inside, only certain wavelengths fit. This creates a pressure difference with more activity pushing from the outside than from within, forcing the plates together. It is a real, measurable force arising directly from the manipulation of vacuum energy. But notice the critical difference from the Unruh effect. The Casimir effect doesn't create energy. It merely shapes the existing, ever-present fluctuations to produce a tiny force. It is like using a dam to channel a river's flow to turn a water wheel. You aren't creating the water, you are just redirecting its existing motion to do work. The Unruh effect is different. It doesn't just channel the zero-point field. It changes what an accelerating observer perceives that field to be, transforming its appearance from a balanced hum into a thermal glow. Both are real, but they are different faces of the same quantum coin. So why can't we just plug into this infinite sea of zero-point energy and power our civilization? The answer lies in that word, infinite. The vacuum energy is everywhere in equilibrium. It is like trying to get a hydroelectric dam to work on a perfectly flat, placid lake with no current. To extract net energy, you need a gradient, a difference in energy from one place to another, like water flowing from high to low. The zero-point field in its natural state has no such gradient. It is the same intense buzz everywhere. Creating a usable gradient like the pressure difference in the Casimir plates requires putting energy in to set up the conditions, and you will never get more work out than you put in. The vacuum is not a battery to be drained. It is more like the molecular vibration of the air in a room. It is there. It is enormous if you could sum it all up, but it is fundamentally disordered and unavailable to do organized work. Science fiction loves the idea of vacuum energy engines, but mainstream physics sees a fundamental thermodynamic wall. The zero-point field is the stage, not the actor, the canvas, not the paint. The Unruh effect gives us a fleeting, personal glimpse of that stage's inherent warmth, but it reminds us that feeling the heat is not the same as capturing its fire. Our dream of a fuel-less engine dissolves against the unforgiving math of reality. Yet the question lingers, what would life be like if we could live within that math? Picture a future centuries from now where humanity has mastered interstellar travel not with warp drives, but with patience and constant, gentle thrust. Generations ships cruise between stars, their engines maintaining a steady one gravity of acceleration for years on end, providing comfortable artificial gravity for the crew. In this world, acceleration is not a brief, violent event, but the steady background hum of existence. And here, the Unruh effect transitions from a theoretical phantom to a subtle, ever-present environmental factor. For these travelers, the quantum vacuum outside their hull is not cold. According to the equations, at a constant one gravity, the void would have a temperature of about 4/trillionths of a degree above absolute zero. This is unimaginably faint, a whisper so quiet it is drowned out by the cosmic microwave background, the leftover heat from the Big Bang itself. So no, the hull would not glow with perceptible heat, and the crew would not need special shielding against this quantum thermal bath. It is far too weak to affect human biology or even most conventional sensors. The vacuum's warmth is not a direct threat, but its existence becomes a fundamental part of their engineered reality. It is a baseline, a quantum signature of their state of motion, as intrinsic to their frame of reference as the artificial gravity beneath their feet. This has profound implications for their technology, especially the ultra-sensitive quantum systems that would form the backbone of their ships' computers and sensors. For us on Earth, quantum bits are plagued by thermal noise from our warm environment, which is why we cool them to near absolute zero. For our interstellar travelers, even in the depths of space, their constant acceleration creates its own intrinsic thermal environment, a 4/trillionth of a degree hum from the universe itself. Their most advanced quantum processors would have to be designed to account for this, to differentiate between the noise of their own motion through the quantum foam and the signal they are trying to process. It becomes a built-in source of error, a thermodynamic tax on coherence imposed not by their equipment but by their journey. Could this faint whisper ever be harnessed? The idea of using it as a power source is tantalizing but faces the same thermodynamic wall as all vacuum energy concepts. The Unruh radiation at one gravity is uniform, a perfectly bland thermal bath with no gradient to exploit. It is like trying to power a mill with a perfectly still, lukewarm pond. To extract work, you need a difference, a hot side and a cold side. The ship's hull, bathed equally in this phantom glow, offers no such difference. However, it might become a consideration for waste heat management in the most delicate of balances. The ship's own systems generate heat that must be radiated away into the cold of space. But if space itself has a theoretical temperature, however minuscule, that sets a slightly higher floor for how cold your radiators can possibly get. It is an infinitesimal effect, but on century-long voyages where every joule of energy is accounted for, even the 4/1,000,000th of a degree warmth of the accelerated vacuum becomes a line in the engineer's ledger. The true lifestyle implication is more philosophical. For these starfarers, the lesson of Unruh is woven into daily life. They live the truth that empty space is an illusion, that their perception of reality is fundamentally tied to their state of motion. The void is not an inert backdrop but an active participant in their journey, its quantum nature responding to their chosen path. They inhabit a universe where the very act of going somewhere, of sustaining acceleration, leaves a thermal fingerprint on the cosmos. Their reality is literally warmer than the reality of those they left behind on a stationary planet. A permanent, subtle reminder that in this universe there is no single, privileged frame of reference, only the perspective you carry with you. This faint thermal whisper from our own motion finds a cosmic echo in the grandest motion of all. The entire universe is accelerating, not in a straight line, but in its very expansion, driven by a mysterious force we call dark energy. And just as constant acceleration through space creates a personal Rindler horizon, the accelerating expansion of the cosmos creates vast cosmological horizons on the largest scales. These are not boundaries in space, but in time, limits to how much of the universe we will ever be able to see, as light from increasingly distant galaxies simply cannot keep up with the stretching of space between us. We are, in a very real sense, accelerating away from everything else. This situation creates a profound parallel. Some theoretical models suggest that an observer in a universe dominated by dark energy like ours should perceive a faint thermal radiation associated with this cosmological horizon. This predicted glow is sometimes called de Sitter radiation, named for the shape of an exponentially expanding universe. The mathematics bear a striking family resemblance to the Unruh and Hawking effects. Once again, a horizon, this time carved by the universe's own expansion, scrambles the quantum vacuum and is predicted to generate a gentle heat. This idea places the Unruh effect into its ultimate context, not as a quirk of rocket ships, but as a universal principle linking acceleration, horizons, and temperature at every scale, from a laboratory tabletop to the edge of the observable cosmos. The cosmic microwave background, that ancient afterglow of the Big Bang that fills the sky, has a temperature of about 2.7 Kelvin. It is the dominant thermal reality of our universe. The predicted temperature from our de Sitter horizon, however, is almost unimaginably colder, a minuscule fraction of a degree above absolute zero, far too faint to ever detect against the roar of the older, hotter background. Yet the theoretical connection is deeply suggestive. It hints that the very structure of space-time, when it possesses any kind of horizon that hides information forever, must pay a thermal price. Our accelerating universe, with its ultimate future horizon, may itself be sitting in a bath of its own making, a quantum glow born from its endless expansion. This transforms our understanding of the vacuum. It is not a static emptiness, but a dynamic medium whose apparent properties, cold or warm, inert or energetic, are a dialogue between the quantum fields and the geometry of the cosmos itself. We are not passive inhabitants of space. We are participants in a thermodynamic relationship with the universe's shape and fate. The warmth an astronaut might one day feel from acceleration is a tiny, local reflection of the same cosmic principle that may govern the ultimate heat-death of everything. This cosmic echo of warmth forces us to re-examine one of Einstein's most elegant ideas. His equivalence principle is a cornerstone of general relativity. stating simply that the force you feel from gravity is indistinguishable from the force you feel from constant acceleration. Stand in a closed box on Earth and you feel a steady pull downward. Place that same box in deep space and accelerate it at 9.8 meters per second squared, and every experiment you perform inside will give the same results. The two situations are, according to Einstein, perfectly equivalent. Yet the Unruh effect introduces a fascinating and subtle crack in this perfect mirror. It tells us that an observer constantly accelerating in flat, empty space will perceive a thermal bath from the quantum vacuum. So, by the logic of equivalence, an observer standing still in a gravitational field like you, right now on Earth, should perceive the same thing. The gravitational field should make the vacuum around you feel warm, but it does not. You are not bathed in a detectable glow of Unruh radiation from Earth's gravity. This is not a failure of the equivalence principle, but a revelation of its limits. The principle holds perfectly for classical physics, for the motion of balls and pendulums and light beams. But when we bring quantum field theory into the picture, the equivalence becomes more nuanced. The thermal state perceived by an accelerating observer is a quantum field theoretic result. For the equivalence to be complete in the quantum realm, a stationary observer in a gravitational field should see a similar thermal state. And in a stunning theoretical leap, this is exactly what Hawking showed for the extreme gravity of a black hole. The stationary observer far away sees it glow. But for the gentle gravity of Earth, the predicted Unruh temperature is so infinitesimally small it is lost in the noise of the universe. More importantly, the mathematical descriptions differ. The accelerated observer in flat spacetime has a well-defined thermal spectrum. The observer at rest in a gravitational field like Earth's is in a much more complicated situation. The spacetime is curved, and the concept of a universal vacuum state becomes ambiguous. This subtle difference is not a trivial detail. It is a testing ground, a precise point of tension where quantum mechanics and general relativity rub against each other. The Unruh effect, born from quantum fields in flat space, gives us a clean, calculable prediction. General relativity describes gravity as curved spacetime. Unifying the two means understanding how that curved spacetime modifies the quantum vacuum in a way that smoothly connects the Unruh result for acceleration to something else for gravity. That something else is the open question. Does the equivalence principle ultimately hold in the quantum domain, meaning we just need to calculate the correct thermal state for a gravitational field more carefully? Or does it break down, requiring a modification to either quantum field theory or to our understanding of gravity at the most fundamental level? This makes the Unruh effect far more than a curiosity. It is a controlled experiment in theory, a precise probe. By studying the thermal consequences of acceleration, physicists are stress testing the bridge between Einstein's geometric universe and the probabilistic, fluctuating world of the quantum. Any successful theory of quantum gravity must be able to explain why acceleration creates this heat and exactly how that translates or fails to translate into the experience of standing on solid ground. The void warmth is a whisper challenging two pillars of modern physics to finally speak the same language. That subtle crack in Einstein's equivalence principle widens into a chasm at the edge of a black hole, igniting one of the most heated debates in modern physics. It is called the black hole information paradox, and at its heart lies a question that threatens the foundations of quantum mechanics. Is information ever truly destroyed? Quantum theory says no. Every interaction, every particle collision is in principle reversible. The information about what fell into a black hole, the specific arrangement of atoms that made up a star or a spaceship, should be encoded somehow in the Hawking radiation the black hole slowly emits. But Hawking's original calculation suggested the radiation was purely thermal, random noise carrying no specific details. If the black hole evaporates completely, that information seems to vanish forever, erased from the universe. This is the paradox, a direct conflict between the unitarity of quantum mechanics and the semi-classical physics of black holes. To resolve it, physicists have proposed some radical ideas, and one of the most startling is the firewall paradox. Imagine you are an astronaut now crossing the event horizon of a black hole. According to classical general relativity, you would feel nothing special at that invisible boundary. You would float right through. But the firewall hypothesis suggests something far more violent. To preserve the information of what fell in, some theories require that the quantum fields at the horizon be in a highly energetic, scrambled state. For you, the infalling observer, this would not be a smooth vacuum. Instead, you would encounter a searing wall of ultra-high-energy radiation, a literal firewall of intense particles the moment you reach the horizon. You would be incinerated immediately. This is where the Unruh effect becomes a crucial lens for understanding the debate. Recall that an accelerating observer, like someone hovering just outside a black hole's horizon using rockets, perceives the vacuum as a warm thermal bath, the Unruh Hawking radiation. From their perspective, the horizon is a gentle glow, but the equivalence principle says that the infalling observer, who feels no acceleration as they cross, should perceive that same horizon as empty space. The firewall argument says these two pictures cannot both be true if information is to be saved. The quantum correlations necessary to preserve information might force the vacuum state at the horizon to be so entangled in a specific way that, for the person falling in, it no longer looks empty. It looks like a raging inferno. In this speculative picture, the firewall is an extreme, lethal manifestation of Unruh Hawking radiation, but only for the infalling observer. It is as if the act of preserving cosmic information for the outside universe demands a catastrophic breakdown of the equivalence principle for the individual at the point of no return. The Unruh framework is essential here because it gives physicists a way to calculate what different observers see. By carefully modeling the quantum field states for the hovering and the falling observer, they can test whether a smooth, empty horizon is mathematically compatible with the radiation carrying away information. So far, the results are deeply puzzling, suggesting we may have to give up one of our most cherished principles, either the equivalence principle, the unitarity of quantum mechanics, or the idea that black holes have a smooth interior. The warmth of the void, first glimpsed in a simple thought experiment about acceleration, has become a blazing spotlight on the most profound conflict in our understanding of reality, forcing us to ask what the universe values more, the experience of a single observer or the permanent preservation of every bit of information it has ever contained. The firewall paradox exposes a raw nerve where our two greatest theories of reality, quantum mechanics and general relativity, refuse to reconcile. To navigate this conflict, physicists need a common language, a framework that allows quantum fields to speak in the curved geometry of Einstein's universe. That framework exists, and it is called quantum field theory in curved spacetime. Think of it as a temporary diplomatic agreement between two powerful but stubborn kingdoms. On one side, you have the quantum realm, which describes particles as excited states of invisible, omnipresent fields. On the other, you have general relativity, which describes gravity not as a force, but as the curvature of spacetime itself, shaped by mass and energy. Quantum field theory in curved spacetime does not attempt to unify them into a single, perfect theory. Instead, it makes a pragmatic compromise. It says, let us treat gravity classically as a fixed, curved background stage, the way Einstein described it. Then, let us place our quantum fields onto that stage and see how they perform. It is quantum mechanics taking a bow on the warped geometry of a black hole or the expanding fabric of the cosmos. This approach is incredibly powerful because it allows us to ask precise questions about quantum phenomena in gravitational settings, questions that would be impossible to answer otherwise. How does a quantum field behave near a singularity? What happens to the vacuum during the rapid inflation of the early universe? And crucially, what does an accelerating observer see when moving through that vacuum? The Unruh effect is not just a quirky prediction. It is one of the cleanest, most elegant results to emerge from this entire framework. In the flat spacetime of special relativity, where there is no gravity, the calculations are precise and unambiguous. They show definitively that the concept of a particle or even of empty space is not absolute. It depends on the observer's motion. Quantum field theory in curved spacetime then takes this result and asks, what changes when the stage itself is no longer flat but curved by gravity? This is how we get Hawking radiation. The framework applies the same quantum principles, the same idea of horizons scrambling the vacuum, to the curved spacetime around a collapsing star. The Unruh result acts as a guiding light, a simpler case that builds intuition for the more complex gravitational one. So, while it may sound like an obscure branch of theoretical physics, quantum field theory in curved spacetime is the essential toolkit for exploring the quantum edges of our universe. It is the language we use to translate between the probabilistic flicker of the quantum world and the smooth, geometric curves of gravity. Every insight about phantom radiation, whether from acceleration or from a black hole, is written in this language. It represents our best, most rigorous attempt to understand the cosmos before we possess a complete theory of quantum gravity. The final theory that would not just place quantum fields on a curved stage, but would show how the stage itself is built from quantum threads. For now, this framework is our map through the strange territory where nothing becomes something, and where the warmth of the void whispers the secrets of spacetime itself. The very idea of a true vacuum begins to dissolve under this scrutiny. If one person's empty space is another's warm bath, then what is the universe like when no one is looking? The Unruh effect forces us to confront an unsettling but profound possibility, that the bedrock concepts of physics are not descriptions of an objective stage, but of a relationship between the stage and the audience. A particle is not an independent thing you can point to like a rock on a path. It is more like a note in a symphony, only discernible through its interaction with the instrument of observation. And in this case, the instrument is not just a detector, but the entire state of motion of the observer, their reference frame. There is no single, God's eye view of the quantum vacuum from which to declare its true nature. Instead, there are only perspectives, each equally valid, each telling a different story about what is real. This is the radical relativity of reality that emerges from the quantum world. It echoes the central lesson of Einstein's theory that time and space are not absolute, but are woven together differently for different observers. The Unruh effect extends this principle into the quantum realm, suggesting that even the most fundamental constituents of matter and energy are part of that relational tapestry. For centuries, science sought to peel away subjective experience to reveal an objective world underneath. But here, at the frontier, the observer is woven back into the fabric of what they observe. Your motion does not just change what you see, it changes what is for you. So does the universe have a true vacuum state? From the framework of quantum field theory, the answer leans toward no. There is no privileged, motionless frame that defines the ultimate emptiness. There is only a collection of possible states, each corresponding to a possible history of motion through space-time. The vacuum is not a noun, it is a verb, a process defined by a relationship. This shifts physics from a quest for absolute truths to a map of consistent perspectives. It is not that anything goes, the laws are rigid and mathematical. But those laws govern connections, not solitary objects. They tell you how the reality of a speeding astronaut connects to the reality of a stationary planet, not which one is the correct version. This philosophical shift has ripples far beyond the lab. It challenges our deepest intuitions about a world out there, separate from ourselves. If the act of accelerating can summon particles from the void, then reality is not a static painting we admire, but a dance in which we are active participants. The warmth of the Unruh glow is more than radiation. It is the signature of our engagement with the cosmos, a permanent reminder that to be an observer in this universe is to be a co-author of the scene. That philosophical shift from absolute reality to relational perspectives is pure fuel for the storyteller's imagination. While the precise mathematics of the Unruh effect remains in textbooks, its core idea, that motion can summon energy from the void, has powerfully influenced the landscapes of science fiction. You will not often hear a character mention Unruh by name, but you can feel its presence in the whispered promises of futuristic technology. Think of the constant thrust drives in series like The Expanse. The Epstein drive that allows ships to travel across the solar system with months of steady acceleration, providing gravity by the push of its engine, is a narrative embodiment of a universe where sustained thrust is a lifestyle. While the show focuses on the human drama of G-forces and travel times, the underlying implication is a mastery of propulsion so efficient it approaches the dream of the Unruh thought experiment, a ship that can accelerate for years. It makes that imagined future feel grounded, a world where the thermodynamic and relativistic consequences of constant motion are simply part of the engineering. The concept goes further, often morphing into the tantalizing idea of the reactionless drive or quantum vacuum thruster. In countless novels and films, you will encounter engines that claim to push against the fabric of space itself, to harness the zero-point energy of the vacuum. This is almost always a dramatic oversimplification of the delicate physics behind the Casimir and Unruh effects. Real vacuum energy is a balanced, uniform sea, notoriously difficult to tap for thrust. But the narrative leap is understandable and compelling. It transforms the empty blackness of space from a barren nothing into a potential something, an infinite reservoir of power waiting to be unlocked. This provides a perfect solution to one of science fiction's biggest hurdles, the tyranny of the rocket equation. If you do not need to carry reaction mass, if you can instead push off the quantum foam, the entire galaxy opens up. It is a dream of ultimate freedom, and it stems from a kernel of real, if wildly exaggerated, physics. These stories thrive on the mystery and promise of quantum phenomena. The Unruh and Hawking effects introduce a universe that feels alive with hidden activity, where emptiness is an illusion. For a writer, this is a gift. It allows for technologies that blur the line between engineering and metaphysics, engines that glow with an ethereal light not from combustion, but from stirring the quantum vacuum itself. It enables narratives where perception defines reality, where a ship's drive might not just move it through space, but subtly alter the quantum context around it. This makes the future feel stranger, more wondrous, and more deeply connected to the fundamental truths we are uncovering today. The sci-fi version may be a simplification, but it serves a vital purpose. It translates an abstruse physical principle into a visceral sense of possibility. It allows audiences to feel, in their gut, that the universe is not a cold, empty void, but a vibrant, energetic field of potential, and that our future among the stars might depend not on bigger fuel tanks, but on learning to speak the subtle language of that quantum sea. The frontier of this research is not a quiet place. Laboratories around the world are buzzing with activity, designing ever more clever experiments to coax a signal from the quantum noise. Teams at institutions like the University of Nottingham, the University of British Columbia, and the Weizmann Institute of Science are pioneering new analog gravity setups. They are moving beyond flowing water to even more controlled environments, like superfluid helium or ultra-cold atomic gases trapped in laser lattices. In these systems, researchers have unprecedented command, able to tune parameters with exquisite precision to simulate not just a simple horizon, but the complex dynamics of an accelerating observer. The goal is to create a cleaner, louder signal of the analog Unruh radiation, something that rises definitively above the background noise of the experiment itself. It is a painstaking game of quantum whispers, but each refinement brings us closer to confirming the fundamental mechanism. Alongside these tabletop universes, theorists are performing mental gymnastics of their own, pushing the calculations into wilder territory. The classic Unruh effect assumes perfect, uniform acceleration, a smooth, endless push, but what happens during more realistic, jerky motion? Physicists are now modeling non-uniform acceleration, where the rate of push changes over time. This is far more complex, as it can create not one, but multiple overlapping horizons in the quantum field. The predicted radiation becomes non-thermal, losing its perfectly bland character and potentially carrying specific signatures in its spectrum. These calculations are crucial because nothing in the real universe accelerates with perfect smoothness forever. Understanding these messy scenarios is key to connecting the pristine theory to any potential future detection in the chaotic motion of real particles or cosmic objects. One of the most exciting new frontiers is called entanglement harvesting. This idea asks a fascinating question. If the vacuum is full of quantum entanglement, like a web of invisible connections, can two separated observers, by simply accelerating or moving in clever ways, harvest some of that entanglement for themselves? Imagine two astronauts, Alice and Bob, floating in the void. They are not initially entangled, but if they both perform specific accelerated maneuvers, their interaction with the quantum vacuum can actually create a new, shareable quantum link between them. They can, in theory, extract entanglement from the fabric of space itself. This is not just a curiosity. It probes the fundamental structure of quantum fields and could have implications for how we understand information and correlation in the cosmos. It turns the vacuum from a backdrop into a resource, a cosmic well of potential connectivity that might be tapped through motion. The tendrils of this research even extend into the world of materials. Condensed matter physics, which studies the behavior of solids and liquids, is finding surprising parallels. Certain exotic states of matter, like topological insulators or specific superconducting phases, have excitations that behave mathematically like particles in a curved spacetime. Researchers are exploring whether concepts from the Unruh effect can describe the thermal noise experienced by quasiparticles, collective excitations within a material when they are effectively accelerated by strong electric fields or other forces. This cross-pollination is powerful. It means that insights from the cosmos could one day help us design new materials with unique electronic properties, and conversely, observations in a lab crystal might shed light on the physics of horizons. Names like Silke Weinfurtner, who leads groundbreaking fluid experiments in Nottingham, or theorists like Robert Mann and Achim Kempf, who delve into the deep structure of quantum fields and acceleration, are at the vanguard. They are not seeking the phantom heat directly, but building the intellectual and experimental tools to prove, once and for all, that the universe obeys this strange relational rule. Every refined analog, every complex calculation of non-uniform motion, every proposal for harvesting entanglement is a step toward a profound validation. It is the meticulous work of mapping a theoretical ghost, of proving that the warmth of the void is not just a beautiful idea, but an inescapable feature of a reality where our motion writes the laws of physics around us. The true value of this phantom warmth lies in the questions it forces us to ask. The Unruh effect is far more than a bizarre prediction about empty space. It is a master key, a fundamental stress test for the very pillars of our understanding of reality. At its core, it is a rigorous mathematical consequence of merging quantum mechanics with Einstein's special relativity. It shows us that these two great frameworks, when combined, produce a startling and non-negotiable result: that motion through the quantum vacuum has thermal consequences. This is not a suggestion, it is a direct implication of the math. If you believe in quantum fields and you believe in the relativity of motion, then you must accept that an accelerating observer will feel this heat. This makes the effect a critical benchmark. Any attempt to build a new theory, to modify quantum mechanics, or to tweak relativity must be able to reproduce or explain this result. It is a fixed point in the theoretical landscape, a lighthouse that guides us away from dead ends. The Unruh effect does not sit quietly in its own corner of physics. Its tendrils reach out and touch everything. Through its intimate link to Hawking radiation, it forges a deep connection to gravity and thermodynamics, suggesting that heat, information loss, and horizons are universal concepts, whether created by a rocket engine or a collapsing star. It blurs the line between acceleration and gravity, probing the limits of Einstein's equivalence principle and asking whether it holds in the quantum realm. This probing is essential because the ultimate goal of modern physics is a theory of quantum gravity, a single framework that can describe the universe from the smallest particle to the largest cosmic structure. The Unruh effect is one of the cleanest, most controlled environments we have to study how quantum fields behave in settings that hint at gravity, acting as a training ground for the more complex physics of black holes and the Big Bang. But perhaps its most profound lesson is philosophical. It shatters the classical notion of a passive, objective universe. The Unruh effect teaches us, in no uncertain terms, that the vacuum is not a static emptiness. It is a dynamic, seething medium whose apparent properties, cold or warm, empty or full, are not absolute truths. They are relationships. They depend fundamentally on who is looking, and more specifically on how that observer is moving. The act of observation cannot be separated from the state of the observer. There is no single, God's eye view of the quantum world. This relational reality is a cornerstone of modern theoretical physics. It moves us from a universe of solitary objects to a cosmos of connections and perspectives. The warmth of the void is the signature of that connection, a permanent reminder that we are not mere spectators in this cosmic theater. By the very nature of our journey, by our acceleration or our stillness, we co-author the reality we perceive. In the quest to understand everything, from the fabric of space-time to the fate of information, this strange glow from nothing is not a side note. It is a central character, whispering the deepest secrets of how the universe truly works. The void is never truly empty, and our journey through its hidden warmth has been a voyage across the scales of reality itself. We began with a simple, staggering idea that constant acceleration could make the perfect vacuum glow with heat. This Unruh effect is more than a mathematical curiosity, it is a gateway. It led us to the quantum foam, that seething foundation of all existence where particles flicker in and out of being. We saw how acceleration carves a horizon in space-time, a Rindler horizon that scrambles that foam and pays for the lost information in thermal radiation. From there, the connections deepened, revealing the Unruh effect as the conceptual twin of Hawking radiation, linking the heat of motion to the heat of a dying black hole. We followed the threads into debates about the nature of reality itself, questioned whether inertia might emerge from the vacuum, and dared to dream of engines that push against the quantum sea. We even saw its potential echo in the accelerating expansion of our entire cosmos. Through it all, one truth stands clear: the Unruh effect is a master key. It stresses the union of quantum theory and relativity, probes the limits of Einstein's equivalence principle, and serves as a crucial training ground for the elusive theory of quantum gravity. While we may never feel its phantom warmth directly, its value is immeasurable. It forces physics to be relational, teaching us that the universe is not a static stage with a single script. Reality is a dialogue, a tapestry of perspectives woven between observers and the vibrant, energetic fields they move through. This understanding shapes everything. It guides how we might one day build quantum computers for interstellar travel, how we interpret the fate of information at the edge of a black hole, and how we ultimately seek a complete description of nature. The cosmos is far stranger, more active, and more interconnected than our everyday senses suggest. These explorations at the frontier are not just academic, they are the first maps of a future we are destined to build. What aspect of this journey struck you as the most mind-bending? Was it the relational nature of reality, the connection to black holes, or the futuristic implications? Share your thoughts below, and if you crave more voyages to the edges of understanding, be sure to subscribe for our next exploration into the science of tomorrow.